Okay, so now I'm going to give you some example problems from each of the individual gas laws, and then one for the ideal gas law itself. And I'm going to show you how to do these based on just that one type of equation that we just set up in that last video. So in other words, P1 V1 over N1 T1 equals P2 V2 over N2 T2. And if we look at each of these questions individually, the first thing we need to do is figure out what is it that's held constant, take that out of our equation, and then just figure out what the problem is. So, as a demonstration of Gay-Lussac's law, where the pressure is the amount of gas that's directly proportional to temperature if volume is constant, we have an example problem here where a 6.25 liter container holds 3 atms of gas at 32 degrees Celsius. What is the pressure of the container if it is heated to 55 degrees? So in this case, both the number of moles and the volume are constant. So what we can actually do is just disregard both the moles and the volume because they're constant. And that's how we derive our equation that we're actually going to use. But be careful, remember how I said temperature is in Kelvin. So the next thing we need to do is change our temperature to Kelvin. Both of them. Make sure you do that. So let's get in that practice. All you have to do is add 273.15 and you get the values here and here. And then you just plug numbers into the equation and solve. So 3 atms is where it's 305 Kelvin. Make sure that those are still talking about the first situation of gas that you have there. You're looking for what the second pressure is, and that's where the temperature is. And so you solve for that P2 and you get 3.23 atms. In our next problem, we're going to demonstrate what Boyles Law demonstrates, and that is the volume of a gas is directly proportional to temperature when pressure is constant. The number of moles is also constant, even though that's not stated outright. So let's see, the example problem is that if 100 milliliters of a gas at 27 degrees Celsius is equal to 0 degrees Celsius, what is the new volume? So pressure and moles are not mentioned. Therefore, we assume that those are constant. So we can take P1 and P2 and cancel them out. And we can take N1 and N2 and cancel them out. And then we just get our equation. So this is what we're going to use. Is V1 over T1 equals V2 over T2. But again, we have to convert from Celsius to Kelvin. So we add 27 degrees to 273.15 and we get 300. Now, 0 degrees Celsius, we should also convert to Kelvin, but that's 0 plus 273.15, so I think we can do that, right? The other thing here that you need to recognize is that liters, or you're given milliliters instead of liters. So if you want to keep it in liters, you need to convert over to liters as well. And you all know how to do that. So plug and chug into your equation. V1 is 0.1 liter over 300 Kelvin is equal to V2, whatever that amount is, over 273.15. When you solve, you have to make sure that you know what your units are, because this is in liters. If you convert back, you can get that into milliliters. On the next problem, we're going to look at Boyles Law. And Boyles Law states that the volume of an amount of gas, in other words, some number of moles that doesn't change, at a constant temperature is inversely proportional to pressure. So when one goes up, the other one goes down. What we're told here is that moles and temperature are constant. Let's read our problem and make sure that that's still the case. You fill a balloon with 0.5 liters of air. That exerts 1.3 atmospheres of pressure on the balloon. The balloon will pop at 2 atmospheres of pressure. At what volume does the balloon pop? we don't mention anything about moles or temperature here. So I start with this formula, I cross out moles and temperature, and that means just pressure and volume are what we're going to use. So we don't need to convert anything from Kelvin because it's already crossed out, temperature's not being used. So we just say 1.3 atmospheres times 0.5 liters is equal to 2 atmosphere times an unknown second volume. And what we find is that that is a decreased volume. This is kind of like stepping on a balloon. When you compress the balloon and get it smaller, it puts much more pressure on the outside of that balloon, and that's what makes it pop. Okay. Next, we have Avogadros Law. So Avogadros Law states that the volume and number of moles of gas are directly proportional if pressure and temperature are constant. So let's make sure that that's actually what is going on in this example. You have a 3.4 liter balloon with 0.2 moles of gas. If you add 0.05 moles to the balloon at the same pressure and temperature, we got a hint there. How does the volume change? So we're given the same pressure and temperature, which tells me that pressure and temperature cancel out. So this is the equation that we're going to use in this case. There's no need to convert anything. We don't have any temperatures that we need to convert in this case. We're already in liters, so we're good to go. So 3.4 liters over 0.20 moles is equal to V2 over 0.25 moles. Where did I get that value? Remember, we had our 0.20 moles and we added 0.05. So adding those two together is where that came from there. And then you just solve for V2 and you find that you have 4.3 liters. Now, it is worth saying that there is also something called a combined gas law, and that's going to use 3 of the 4 variables. And so sometimes you might see something like that. It's the same process, so don't worry about that. Just, when you don't hear about or read about a change in one of the variables, that means that it's constant, or it will tell you that something is constant. These situations are comparing one form of gas to something changed to another form of gas. On the other hand, when you're using the ideal gas law by itself, it's usually discussing one type of gas under one set of situations. So here's an example. If a gas occupies 3.5 liters of, I don't know why I put it as of gas there again, sorry about that. It consists of 1.2 moles of gas at 23 degrees Celsius. What is the pressure of the gas? So we need to figure out what's our equation that we're going to use in this case. We're not comparing two things, we're just saying, what is the pressure when you have a known volume, number of moles, and temperature? Now, we can just use PV equals nRT, and we're looking for pressure. We need to switch our temperature into Kelvin, and we need to make sure that our pressure is going to be in atmospheres. If instead you need to switch it to something else like torr, you can find this in atmospheres and then convert it, or you can use a different R value that actually has it already in torr, for example. So I converted this to Kelvin already, and then it's just a plug and chug. So our pressure times 3.5 liters is equal to 1.2 moles. That's our N. Here's our R value, and then here's T. So when we solve for that, pressure is 8.4 atmospheres, which is actually really high. You don't want to be under a pressure like that. Thank you very much.